Hello, my name is Matthew,
I'm Lisa.
and we're with the Tampa Hillsborough County Public Library, just how we rehearsed. We welcome you to the program tonight, which is TESS Talk with Natalia Guerrero into the Interstellar Unknown. So tonight we're going to do just a couple of quick things, then we'll hear from Natalia, and then we'll do a live Q&A at the end. So like I said, type in those questions to the question section, and we'll be sure to get to those. But before we do our official talk, we're going to go ahead and go to our book shout out. Help us out, Lisa.
Hi, so we've got two great books here for you if you're interested in learning a little bit more about this topic. Almost Astronauts is a great book that talks about the history of 13 female aviators that trained alongside the early Mercury astronauts in the NASA program. So great history there. And the other book is called Constellations. So if you're out in the backyard looking up the night sky and you want to learn a little bit more about what's up there and maybe how some of those constellations got their names, check this book out. They're available in the library, so you can get your physical book there, but you can also download some of these apps and get them right there on your phone, on your tablet, and look at them that way. So the apps are listed on the screen there. We highly encourage you to check those out.
Thank you so much, Lisa. And it's great that we see Access 360 on there because some of you may be familiar with Hoopla and Libby and Overdrive, but Access 360 has an excellent collection and it's not as utilized as some of the others. And so definitely check that out if you're not familiar. So before we officially begin, we're going to just do a quick poll. All right. So are you familiar with NASA's TESS project? Please vote and let us know. Gonna give you a few more seconds. All right, and we're gonna count down. You have a few more seconds to vote. 5, 4, 3, 2, and 1. Okay, I'm gonna share the results. Okay, Natalia, it's pretty, well, somewhat evenly split here, but definitely more no's than yes. So I think they're in for a real treat tonight because they're going to get to hear all about you and your work with TESS. So now Lisa and I are going to turn off our cameras, although I'm still going to have on my NASA tie from the Kennedy Space Center. I'll be wearing proudly in support of our science night. And we will rejoin you, Natalia, for the Q&A.
Sounds great. So good evening, everyone. My name is Natalia Guerrero. I work at MIT in Boston as a researcher of exoplanets for TESS, which stands for the Transiting Exoplanet Survey Satellite. It's a space telescope that looks for planets around other stars or exoplanets. I'm also really interested in science communication and conveying science through art, as shown by some of the pictures here on this screen. I'm standing in front of the TESS Space Telescope right before it launched back in April of 2018. And since then, I've worked on various creative projects with vocal ensemble, the Lorelei Ensemble, to convey some of the amazing results that TESS has produced. So an exoplanet is a planet around a planet outside our solar system. And before the late 1980s, early 1990s, there was no proof that these existed. And so in the late 80s, early 90s is when we started to find proof of exoplanets. So this field has only been around for the last 30 years, but since then it's exploded. And from only a few handfuls of exoplanets in 1995, 1996 or so, we now know of thousands of exoplanets around all sorts of different kinds of stars all over our galaxy. So I want to show you here and tell you a little bit more about my work on TESS. So this is a picture actually taken by one of the test models of a TESS camera. So this was taken at room temperature in the lab. I was part of the testing team for these cameras, and each time that we needed to turn a camera on, the first thing we did to make sure it was working was take a picture. And so myself and some of my fellow scientists posed for this particular photo. And all of these are astronomers who now work with TESS data and use it to expand their own scientific ideas. And as I was putting together this talk, this photo reminded me of another photo taken about 100 years ago. This was taken in 1918 just a 25-minute walk up the street from MIT at the Harvard College Observatory. These two campuses are not that far away from each other in Cambridge, Massachusetts. And these women here were Harvard computers, or women hired to do sort of the more menial calculating tasks of the observatory. And I want to hone in on this particular woman. This is Henrietta Swan Leavitt. Here she is at work with other astronomer or Harvard computers, astronomers, I think, who were looking very carefully at photographic plates. This was how astronomical images were taken in this time period, the late 1800s, early 1900s. So this was a very slow, very analog process, and to understand what was going on, these plates had to be inspected manually. Hundreds of plates, and she was one of a team of women who was studying these, and she was studying variable stars, so stars that changed in brightness from one plate to another. And so she honed in on a particular type of star called a Cepheid variable, which had a very signature pattern of stellar variability. And so this picture and this study of variable stars reminded me of, in modern times, the TESS team. We also look at thousands of stars in the TESS full frame images. TESS takes images of the night sky and as it orbits the Earth. So 4 space telescope cameras, each camera has a field of view like this. And this camera is focused on the Large Magellanic Cloud. So this is visible from the southern hemisphere of the Earth. And they were looking at the change in brightness of stars over time. And we're also looking at the change of stars' brightness over time. This is a real report that we looked at from a particular star. And this, and I'll talk about this more in a second, is the signature of an exoplanet. So how do we actually measure exoplanets with TESS? So as a planet goes around its host star, it blocks out a tiny amount, less than 1% most of the time, of that star's light. So a small planet blocks out a small amount of light. A larger planet blocks out a larger amount of light. So we call this a light curve, the change in brightness of a star over time. And this gives us information about how far away the planet is from its host star. We can start to make some initial guesses as to what the temperature of this planet might be, and we also get the size of the planet relative to its host star. So I wanted to take a moment to compare the types of the change in brightness that Henrietta and the Harvard computers were looking at and what we're looking at today. I've stretched out so on one side we have the signature of a Cepheid variable, and on the other side we have the signature of a hot Jupiter type exoplanet. So before I say anything more, I want us to take a look at these, take them in, and also listen to them. So Matthew, if you could roll the tape. That was a Cepheid variable, and I think now we're going to listen to the hot Jupiter. So we heard and saw that the variable star sort of changes gradually and without any really big changes in brightness over time, whereas the transit of an exoplanet is this very marked, sudden, short-lived dip in a planet's period. And this is the signature that allows my vetting team that I work with to identify thousands of exoplanets from the millions of stars that TESS has observed. So I always think that this is really cool, that there are so many parallels across time and different methods of astronomical observing. So as I said, TESS has found over 2,400 exoplanet candidates since we started observing in 2018. So this has been an amazing opportunity to catalog this set of candidates so that astronomers around the world can go look at them and better understand what exoplanets are, what kind of stars they appear around, what they're made of. And this is a really interesting time to be in exoplanet astronomy because we're learning so much, but there's still so much work to do. I like to think of this map as a to-do list of thousands of exoplanets that we still have so much to learn about. So Henrietta Swan Leavitt, her discovery of Cepheid variables led to finding a meter stick for measuring the stars that she measured. Their change in brightness was able to be used as a measure of distance because the period at which they changed in brightness was related to their absolute brightness. And you could use that to measure distance. And so other later astronomers, like someone you may have heard of, Hubble, used that to measure the distance to galaxies that were outside of our own, and eventually to realize that the universe was expanding. So that started with this meter stick. So we have lots to learn about what exoplanets will reveal to us and what they will be a meter stick for. So one thing we're already learning about is planets that are in the habitable zone of their host star. So this is one such exoplanet. This was the first Earth-sized exoplanet in its habitable zone that TESS discovered, TOI 700d. And this is this is out here in this green ring, which is the habitable zone for this red star. The habitable zone is often thought of as, or the Goldilocks zone is where the temperature is just right for a planet to have liquid water. So what else can we learn from exoplanets in coming years? So a star that has light shining through an exoplanet's atmosphere, some of that light will get absorbed, but some will be transmitted, and that can be captured by other space telescopes waiting to catch it. So one of those is the James Webb Space Telescope. And so this telescope is about the size of a tennis court and actually hopefully going to be launching at the end of this year in October. And one of the instruments it has on it is a spectrograph, which takes the light coming from a planet, sometimes transmitted through the atmosphere of a star, and splits it up into all of the visible wavelengths. So I have here a spectrograph that shows you a little bit of an idea of what that looks like. It's this rainbow that you can see from a light source. Matthew, are you seeing that?
Yeah, that's coming through.
Great. So that gives you a little idea. This is just a teeny tiny one, but there's a professional grade one on James Webb. So what can we learn from spectroscopy, or the measurement of a star's light? So as the light from a star is transmitted through its atmosphere, it is a series of wavelengths. Some of those wavelengths get blocked out, some get absorbed, as I said. That signature of which ones get absorbed tells you about the different molecules that might be in that exoplanet's atmosphere. And so this gives us a specific fingerprint of what kinds of things might be in that atmosphere, and if those are ingredients for life as we know it here on Earth. Important things like carbon monoxide, water, oxygen, methane. So all of these different methods are pointing us to bigger questions. Henrietta Swan Leavitt was looking for a way to measure distance. We're looking for questions of what are the ingredients for life. And I think a question that that it really is compelling to the imagination. Are we alone? So TESS is going to be leading the way for James Webb and hopefully many telescopes for many years after. And I am just really excited to be able to share with you where we are with exoplanet discovery and a little bit about what's next. Thanks.
All right. Thank you so much, Natalia. What a wonderful talk. And we're going to go ahead and start feeding you some of the questions that are coming in. But first, I have to ask my own, or I have to just admit something, that the James Webb telescope, I'd never seen it written out, and for some reason I thought Webb referred to, I thought James was the last name, and I thought Webb referred to the internet, and so there was some new internet technology involved in that telescope. So I have learned something tonight for sure. But yes, for sure. But relating to that telescope, let's see, what is it? Okay. So what does it take to send a telescope into space? I think you mentioned that one is the size of a tennis court.
Yes.
That's quite a challenge, I would imagine. What are some of the processes that go along with that?
So it takes it actually takes something a little bit akin to origami. So the picture that I showed, that shows the sun shield that blocks out all of the sun's light, fully deployed, but they have to fold it up very carefully so that it will fit in the rocket before it launches, and then unfold again very carefully. So testing that was a big deal. But it also requires a really large rocket, and to launch the spacecraft as close to the equator as possible because it's so massive. So this is actually going to be launching not from the US, but I think from French Guiana.
That's very interesting. And so origami, so the skills related to origami folding has something to do with the engineering design of space equipment and telescopes?
Yeah, that's exactly right.
Okay, I haven't done origami in a million years, so I maybe need to like brush up on that a little bit so that I can have some of those applicable skills. So here's a question. How many stars has TESS looked at approximately, and what percentage of those had exoplanets associated?
That's a great question. So TESS has been mapping almost the entire sky, about 70% of the sky since it started observing, and it's trying to take these wide field images. So it has data from millions of stars. And then we focused in on a small number of stars that we take images of every 2 minutes. And so there's 200,000 stars like that, and then millions of stars that we have the full frame images for that are taken every 30 minutes. Now, from those, we have found about 2,400 planets. So this is a very teeny tiny fraction. We have to search a lot of stars to get even a small yield of exoplanets.
Oh my gosh, I can't believe it's in the millions. And there's still a lot to go, isn't there?
Yeah, this is definitely a big data type of mission.
Okay, so here's another question that came in. So what is the relationship of the James Webb telescope to other telescopes, such as Hubble? Will they complement each other in any way? And there's other, we were talking about that right before the session started. We talked about the Very Large Telescope and a couple of others. What is the relationship? How will they complement each other in terms of what data they bring in?
That's a great question. The idea is that James Webb will be the successor to Hubble. Hubble had a bunch of different instruments on it that could observe stars in different wavelengths, that could do some of these observations of what I alluded to, measuring the light coming through planet atmospheres, or transmission spectroscopy is the scientific term. And James Webb is going to be able to do that, but it's also going to be able to do so much more. I only touched on one of the specific things that James Webb is going to do, but it has all sorts of instruments. So it's going to be, again, like a multi-purpose type telescope that's going to be following in the footsteps of Hubble, basically.
Oh, and so this is okay. So related to that, it's a little bit of a maybe a logistical question. What could delay the that telescope going up? What kinds of conditions or issues might get in the way of a date being set?
Yeah, so some of the things are making sure that everything is working perfectly. So it's gone through all of its testing, it's starting to get packaged up onto the rocket. So making sure it gets to the launch pad on time, checking that the rocket is ready to go, all of that is really important. And so all of that has to happen on schedule. And I learned on the TESS mission, which is itty bitty teeny tiny compared to James Webb. TESS is only the size of a refrigerator. There's a lot of steps that go into sending a spacecraft into space, and a lot of that is making sure that it'll survive launch, and then also working with all of the different teams, because we were working on the cameras, but there's also the spacecraft itself, the rocket, the launch pad. All of that needs to work perfectly for a launch to go on schedule.
It's interesting that you were just talking about that aspect, because another question we had come in was how many people were involved in the process of getting TESS off the ground?
I think altogether, we had around 200 people on the team in various sites. So it was us, Northrop Grumman, which was then Orbital ATK, the NASA team, the Falcon 9 team from SpaceX. It was a big collaboration.
And this is the part of the program where you recite all 200 names from memory. Go.
Oh, there's mine.
Right. Let's see. You talked about a little bit earlier about measuring brightness and what information that would be able to help with in terms of collecting data. How has measuring brightness over time changed, like instrumentation and the way that's approached?
I love this question. This is such a great question because I get to talk about another telescope. So
Okay.
halfway through the TESS mission, there was a data release from this telescope called Gaia, which actually went into space. It's shaped like a top hat, which I love. And it went into space specifically to measure the brightness and distance and spectrum of millions of stars. And so this contributed to giving us much more accurate measurements of stellar brightness, stellar size, stellar temperature for our own calculations of TESS planets, because the more information we have about a star, the better we can make calculations about an exoplanet. So actually, brightness measurements have come a really long way, and getting more and more precise measurements of a star's magnitude or its brightness pretty much it continues to be something that people aspire to.
Oh, that's amazing. So just for clarification, in case anybody wants to learn more, you mentioned so in that piece you mentioned the Gaia telescope. How do you spell Gaia if anybody wants to look it up? Do you know?
Yeah, Gaia.
Gaia.
Yes.
Okay, I'm just throwing that in the chat in case anybody wants to. Oh, it's about to set it in the wrong section. That's why it's not. That's why it's not leaving. All right, there we go. Gaia. Awesome. In your experience at TESS, have you gotten to work with anybody or interact with anybody from previous projects, related projects, I guess I should say? Just to clarify that question.
Exactly. Yeah, that's another awesome question because I get to talk about another space telescope. So TESS is the follow-on to a mission called Kepler, which was a space telescope that looked at a single patch, really small patch of sky, but tried to count up how many exoplanets. It was doing a census of all of the exoplanets it could possibly measure in that little patch of sky to basically give us an idea of how many different kinds of exoplanets are there, around what kinds of stars do they occur. And so Kepler was this amazing mission that ran for many years, about 8 years. And then when two of its momentum wheels, or the parts that help it position itself, broke down, they refigured out how to use the telescope to image a different part of the sky. And that became the K2 mission. And engineers, astronomers, data scientists from that mission have all lent their expertise and knowledge to the TESS mission.
Oh, that's amazing. And let's see. Okay, and one of our backup moderators, Chris, has thrown the link to Gaia so that people can just click right on that and go to it. Yeah, there we go, pushing it up. Well, getting to the last 10 minutes or so of our Q&A section, but and we need to share some contact information. But before we do, I want to bring up Lisa from before when she was talking about our book shoutouts, because I know she has at least one or two questions that she wanted to share with you before we wrap up.
I do. I have two. So my first question is, there are a lot of community science programs where people like you and I can go on, for example, to a site like Galaxy Zoo and analyze all this data that's come in from the Hubble telescope and kind of see what's on there and help the big scientists narrow down what they're looking at. That data is very, very visual, so it's easy for lay people like us to look at it and be helpful with it. When you get the data from TESS, is it something that's a lot more just a computer's crunching numbers on it, or is it something where you can look at it and identify what you want to narrow in on?
Yeah, it's I showed that one screen cap of like one of our data reports for a exoplanet candidate. So that transit light curve is this visual piece of information that we can use, and the shape of the exoplanet transit tells you a lot about what's going on. If it's V-shaped, that might mean that it's two stars going around each other. If it has sort of that like up and down smooth shape, that tells you this is definitely a star doing its own thing. So it is visual in that way. And what we can do once we have hundreds or even thousands of examples is we can train a computer to help us with this. So the first step will be, we often give a full sector or download of data to our machine learning algorithm. We tell it, okay, here you go. Tell us if this light curve looks like a transit or doesn't. And then we'll take the transit light curves and do further classification from there. And so they give us a hand cutting things down from hundreds of thousands to, or tens of thousands to just hundreds of candidates that we can use. And you mentioned Galaxy Zoo. And one of the links on the handout is to Planet Hunters, which is a similar project that is hosted by the same platform, Zooniverse. And what it is a community science project that basically brings what we do as exoplanet candidate vetters to the community. So it's real test data, real test light curves that come down every month because TESS downloads data every month. And you as an individual can look at these, identify transits, and often these end up being real exoplanet discoveries. So one of the longest period TESS planet discoveries to date has been from this Planet Hunters platform. So you can contribute to real exoplanet science like right at home with this
amazing.
platform. Yeah.
Well, that brings me to my next question. It's great that we're going to be at home able to work on this as well. Did you always know that you wanted to do this kind of science, or is this something that you figured out once you were already in college?
I may have hinted at it a little bit in my introduction slide. In high school, I actually really wanted to be a writer. The library was my favorite place to hang out. I'm not just saying that because this is hosted by a library. It genuinely was. I was a big bookworm. I loved reading. I loved writing. And so up until about the middle of high school, I was certain that that was what I wanted to do, was be a writer, an editor or something. And then I took a calculus class and another one, and started getting more interested in engineering, and I took a physics class, and I loved it. I loved the problem solving side. I loved using my brain in that way, and I said, okay, I want more of this. And I also love the questions. I posed a couple of questions at the end of my talk. What are the ingredients for life? Are we alone? Those are questions that I think everyone sort of comes up with at some point, sort of along the lines of like, why is the sky blue? Like those sorts of things we all wonder. And I love that there were still questions out there that don't have answers, or nobody really knows what the answer is. When I was in school, I often felt like there's not going to be anything for us to figure out, like everything's already been discovered. And as I learned more, I realized like astrophysics still has a lot of these unanswered questions, and that was really compelling to me. And that's what drew me to studying physics and astrophysics in college, and then going on to work with TESS.
That's great. Thank you. Matthew, did you have any follow-up questions?
No, we're in the home stretch here. But let's see. Okay, so yeah, we're gonna go ahead and bring up our contact information. Let's see. Okay, there we go. All right, so yeah.
We'd love for you to reach out to us here. We've got our phone number on here, 813-273-3652. You'll be able to reach us there, or at hcplc.org/contact. That on our website has all of our information, including the phone number again, but it also has a link to live chat functions where you can go to Ask a Librarian and chat in real time with one of us. If you want to see some more programs like this, what we have on the calendar coming up, check out our events on the same page, hcplc.org/events, see what we have coming up. And if you want to learn more about TESS, tess.mit.edu has all the information and great resources to follow up on if you have any more questions about the TESS program.
Thank you so much, Lisa. And I'll just share this very quickly. When you just talked about the value of unanswered questions, Natalia, I remember we were talking right before the program began tonight, and I said, oh, there's this Carl Sagan quote. I can't really remember what it is. And you just reminded me. And so I looked it up quickly, and I'll share it as sort of our parting words here, because I think it's really well connected to the work that you and the people that you work with at TESS are really like tapping into. And he wrote that we make our world significant by the courage of our questions and the depth of our answers. So that to me like really speaks to the depth of information that you all are getting in various forms, in words and light sources and sound, those amazing like sort of mystical sounds that we heard earlier on the recording. So thank you for doing that work and for visiting our library and sharing it with us. We really appreciate that.
I'm glad to be here. Thank you for inviting me.
Oh, our pleasure, and hopefully we'll do it again someday. Everybody, thank you very much for joining us for our program. Thank you, Lisa. Thank you, Natalia. And everybody have a great night.
Bye, all.